Yeah, drop, hey, huh.
Yo, what's up guys, this is 𝗪𝗚𝗟𝗡, and in this video we're gonna continue the previous one. If you haven't checked it, go and check it. And in the last video we talked about what a buffer flow is, how it's represented in the memory, inside the debugger, and in this case we're gonna continue with the previous example, which is the bof.c, and now we see that we have a wait function here, a void one that only prints a message, naughty boy, you did your first ret2win. And inside main we see that we have a name buffer, a car name buffer of 0x20 size, and we initialize it with 0. It asks what's your name, boy, and here we see that we have a buffer overflow, as we said in the previous video, because scanf reads unlimited data until it reads a new line. We could have fixed that by doing this here to limit the input size, but in this case we have this common mistake here, and then it prints yo, what up, and our name. So let's go back and compile the program. We're gonna use the flags fno stack protector to avoid having a canary, and no pi, so that the addresses of the binary are not randomized. And what's your name, boy? Again we see 𝗪𝗚𝗟𝗟𝗢, it's okay, yo, what up, 𝗪𝗚𝗪𝗢, but if we do we get a segmentation fault. And let's go inside a debugger and see bmain run, and we continue, we reach our first printf, what's your name, boy, and then we continue and we reach our scanf, we enter AAAAAA, BBBB, CCCC, DDDD. Okay, basically let me A 1 2 3 4 1 2 3 4 5 6 7 8 1 2 3 4 5 6 7 8 1 2 3 4 5 6 7 8, and we see that our data is stored here, and we examine this address and we see our A's, our B's, C's, and D's, and then we see this address here and this address here. If you remember for the previous video, this one is the RBP and this one is the return address. And our payload is represented here, as we can see. The first 8 bytes of the buffer, of the name buffer, are stored here, our A's, these, then our B's, our C's, our D's, like this, and then we have the RBP here, which has this address, and then the return address, which contains this. So right now the return address is this. And to remind you what the return address is where the program intends to go in its normal flow. So this one will go to exit normally, blah blah blah, it will call an exit function and leave. And what happens here, we have an overflow, so we can override this and this with whatever we want. So imagine we continue here and we do 1 2 3 4 5 6 7 8, we add some other A's, and then whatever we write is gonna override the return address. And in our case we have this function that we want to call. So you say, okay, nice, we know what we have to do, we have the offset here, and then what we can write the address of the wait function inside here. Cool, that's what we're gonna do. But first of all, what is the address of win? We need to find it. So one way to do it is by do print wet inside the GDB, or just pwet, The print function will tell us at which address is the function we want. For example, we can do pmain. Okay, this will work only for custom addresses of the binary, not libc addresses. For example, if we do printf, we'll see that we get a libc address and not one that is constant. This one is always randomized because of ASLR. And what is ASLR? ASLR is the same with pi, but for the libc functions. So if we see here and do ldd both, we see that the libc, which is the library that contains all the known functions like printf, puts, scanf, read, blah blah blah. And we see that the main address here is this. If we rerun this, we see that this one and this one are different, because in every new run the program randomizes them. Okay, so we cannot calculate the libc function, printf, and the other ones. And we're gonna talk more about this in later videos, where we're gonna explain the ret2libc technique. But in our case, we just care about these functions, wet and main, more likely wet. And we see, okay, we have this address. So imagine here, after our raise, instead of this, we override the return address to this, and the program will go here and call wet. Simple. Yeah, it's simple, but we cannot enter it like this, because the program will understand this as, okay, 0, and then we have x, and then we have 4 as single characters. What we need to do is actually parse it as bytes. And how we're gonna do that? Imagine we have the classic deadbeef string. Okay, this is a hex value. Hex values are integers, but it's easier to represent them this way. And in order to send this, first of all, this one is 4 bytes, right? 1, 2, 3, 4. The addresses, as we saw here in GDB, for example, if we do again x here, these are 8 bytes. Okay, because we are in a 64-bit system and not 32. So this one should be like 1, 2, 3, 4. This one is an 8-byte address. And we need to do Little-Endian. What is Little-Endian? This one should be written like, you take the last byte first, EF, and then you take the other bytes, BE, then AD, then AD, and then DE, and then \he 0, 1, 2, 3, 4. So this is the way we need to send our data, because the stack works with LIFO, last in first out. So we have to send it as Little-Endian, that means backwards from what we see here. And in order to do that, we can just take, there are many ways to send this address, these bytes. Let's do it manually first. This is the one and only time we're gonna do it like this. So we do the same thing. This is 3 bytes, so we need 1, 2, 3, 4, 5. And the same way we're gonna do 96 \x 11 \x 40, and then damn, and then we need all of these zeros and plus another one. We need it in this format. Alright? Let's try and do it with a simple command line. So we have the printf function, and we tell printf, okay, I need this many A's, this is 32 in order to fill the buffer, plus 8 to overwrite the return address. So if you count them, these are 40. Okay? And after that we tell it, okay, you take this address, the address of wet, and let's have it like this in our format, and pipe the output to the BOF program. So let's say here we do a mistake and we have one less A, segmentation fault, something messed up. But if we take the correct payload, I mean with another junk, we see, what's your name, boy, yo, what up? Naughty boy, you did your first ret2win. This was the simplest ret2win example you will ever see, but I hope I made it clear how and why it works this way. And let's try a more dynamic way to do it. So we're gonna use Pwntools. From Pwn import all. This command here imports Pwntools, and in the first video of the series I have a script that tells you how to install Pwntools and some other stuffs you might need. And let's start by opening a local process of our file, which is bof open local process of the binary. And I prefer doing it this way. fname bof, and here we just do fname, and after that we have to analyze the binary, so we do elf and fname analyze read the binary. So this one actually takes all the addresses, symbol tables and stuff you're gonna need later on. And let's craft our payload first. And we have byte A 0x28. Let's do it even better, more analytically, more in depth. So fill the name buffer with junk, and then we have payload, and we're gonna do B. We need another, let's do this dot 8 overwrite the RBP register. You can also see it here. And after that we need to send our win function. So there are many ways to do it. One way is what we had here. You can send it like this. I definitely do not suggest that. I'm not even sure if this is gonna work. Send wet address, and then r.send line after and this. So what this does, we tell the program send line, so it sends a new line and our payload after it finds this character here, this string, and the space. And after that we tell it, okay, send the payload. And after that we're gonna do r.interactive, so it actually gives us an interactive cell to play and see the output. open interactive cell, and yeah, send payload after the program reads the string. So let's test the first solver, Python solver, and it crashed for some reason. What was it again? Both. What's your name? Boy? Yes. Okay, let's just do send line instead of send line after. It's the same thing, but you don't include this. Send payload, and let's do it again. And we see, naughty boy, you did your first ret2win. So this was the worst possible way to do it, like this, but we're gonna keep it. First way, avoid. The other way, second way, which is okay. We're gonna do payload, and we're gonna have p64. The p64 function does exactly this. It takes an integer, or this hex, and converts it to Little-Endian and adds the necessary bytes. So payload p64, and we take the address of win, which is 401196, like this. We can also add the zeros, but it doesn't matter here. And we run the solver again, and we see, naughty boy, you did your first ret2win. So this also worked. Oh, for the memes, we can just do print so add, and let's do p64 of 0x401196, so we can see how it is actually. As we can see, it's the same thing. 96, 11, 40. 40 seems to be a bit odd, but if you see the ASCII table, man ASCII, the hex 40 is this character, so the program translated to this here. And yeah, it's exactly what we expected. And the third one, which is the more dynamic one, third way, best. And the third way is this, payload p64, and we're gonna do it the most dynamic way, e.sim. So we tell the program go to E is where we analyze the binary here, go to symbol tables and take the address of wet. And this one knows where to get it. It takes this value, which is the address of wet, packs it the same way, so it converts to this and sends it. And let's also test it. And yeah, naughty boy, you did your first ret2win. And that's it. We explained our first ret2win technique, the most simple one, and we also showcased 3 ways in solving it and the manual one, so 4 ways. I hope you guys enjoyed the video and learned something. If you have any feedback, leave a comment. If you like the video, leave a like and subscribe to the channel. And get ready for the next video. It's gonna be a ret2win but with arguments. Thank you guys for watching. See you on the next one. Bye.